All right, so what we've been doing when we've been talking about gravity is called classical gravity. So in the classical treatment of gravity, we use this formula for the force of gravity. And for something like, 400 years, it was okay. And so we could calculate the orbits of planets and rocket ships just by using these concepts. So Kepler's laws and then using the force of gravity. But it turned out that that was incorrect. So the correct way of viewing gravity is by using the general theory of relativity. You should know who was the person who came up with it, Albert Einstein. And so you should know what space-time is. Space-time is the three dimensions of space, so up and down, sideways, in and out, and time. So they fit together. So you really cannot make a measurement of distance without using the concept of time and a stopwatch. And you can't make a measurement of time without including the effects of space in it. So space and time go together to make four-dimensional space-time. Now you don't need to know about the special theory of relativity for the exam, but what you should know is the general theory of relativity. And the general theory of relativity takes into account gravity. And so what it says is that the mass of a star bends, it stretches space and time. So imagine that you've got a bed and it's absolutely smooth on the surface of your bed. Then objects will go in a straight line when you roll them across your bed. But now take a bowling ball, put it in the middle of your bed, and do you notice how the covers are bent, how they're stretched to accommodate the bowling ball? So similarly, the mass of a star bends space and time. And so if you take that tennis ball and you roll it on your bed, it's going to be altered in its trajectory because of the way the covers were being bent by the bowling ball. So similarly, a planet's orbit will be altered by the curvature of space and time caused by the mass of that star. That's what you need to know about general relativity. Okay? And so here are the formulas for general relativity, which of course you do not need to know for the exam. But you should know what a black hole is. So a black hole is going to be a star, and as the star dies, it collapses in on itself, and it does explode as a supernova, but gravity is so strong that it continues to pull the star in until it ceases to exist. And then we say then that this star has turned into a black hole. So physically, the star no longer exists, but it still has all of the gravity that it used to. And so this not only stretches space and time, but it basically ruptures space and time. So you can see how space and time there are going down to an absolute point where the black hole is actually located, the singularity of it. And so this stretches space and time in the extreme. And so there's this little video here, Black Holes Explained, that you can watch that illustrates it. But just have an understanding for what a black hole is, and then what does a black hole do to space and time. All right, so this appendix is not going to be on the exam. This appendix is not going to be on the exam. Okay, how to calculate the orbital speed. It's not going to be on the exam. Okay, how to calculate the orbital escape speed. Not going to be on the exam. Calculating the total energy of the Earth. Not going to be on the exam. Calculating the energy of Voyager 1. Not going to be on the exam. All right, so that pretty much takes care of gravity. Okay, so let's take a break, and when we come back, we will do our review for the final lesson that's going to be on the Unit 4 exam.